Coming. So we have our department alumnus Kevin Wu visiting us, and he graduated from here, working with Akio Arakawa and Bill Stevens back a few years ago. And 2008. 2008. Okay. And working on development of cloud resolving simulation, log simulation. Currently, he's a full professor at the National Taiwan University. And his group is among the few in the world that is actively working on improving models and the GPU logic simulation development. He's recently also worked on machine learning related stuff, focusing on providing physics-based understanding of processes. And he's going to talk to us about the recent development of Taiwan VBM-based framework and you don't want to talk about it.
Thanks everyone for coming. I'm Chen. I'm from National Taiwan University. I have to say that last time with James sitting there listening to my talk is my 270 seminar. I freaked out.
You're welcome.
Yeah, I hope this time's better, but I think I might not be able to answer you about the lines. Maybe next time, yeah. But I'm trying to show you how diurnal cycle Taiwan looks like. So this is a Taiwan island. It's actually a small island. It's about 2 by 4 degrees, so about 4, and a very small island with very steep topography. The highest mountain is about 4 kilometers. So you can imagine that in this kind of area, that's orographic effect dominates in shaping this afternoon thunderstorms. And I like this one because, yeah, there's a vortex building up. And I'm also interested in the Lee vortex shaped by this topography as well. But normally I look into the winter time, so I'm not sure what happens in the summer. That's might be the next topic I'm going to talk about. And today I'm trying to show you that given environment, I named it a more fancy way of saying this. My title is that given environment, atmosphere environment, can we know the development of afternoon thunderstorm? And we want to use the numerical model to understand these processes. So a brief introduction to the department. So in Taiwan, we only have 2 departments of atmospheric sciences. So this is National Taiwan University. So these are our full group, around 15 or 80 people with some specialties, specialists. And that's like a healthy group, I think. And we all do work on atmospheric sciences, so on various aspects. So if you're interested in visiting Taiwan, you can always find someone related to your work. Yeah, I'm working on convection, some of them are working on polar, and some are on the tropical cyclones, high variability, all topics, dynamics, machine learning. I'm looking at the picture to say something related to the then service processes. So it's like a variety of this expertise in this department. And this is my group. So maybe you don't feel this is surprising. All of them are PhD. It's very rare in Taiwan, in my group. Everyone's PhD. So normally in Taiwan, they got a master's degree and then leave. But these are the people that are willing to stay and doing research. Surprise. And they are working on, again, various topics, machine learning, observations, everything. And my personal interest is on this model development. So some of them are working on this GPU or CPU-based different algorithms improving the efficiency of the models. Yeah, it's a big group. So it took me like 15 years to build out this group in Taiwan. Okay, so back to the topic I have. This is actually the slide I took from my PhD defense. Back in the days, we are trying to understand what's going on in the diurnal cycle of the land. So you can imagine that this diurnal cycle process is comprised of a variety of scales, starting from this surface fog, shallow cumulus, shallow convection, some deep convection, and some organized afternoon thunderstorms. So a lot of processes are going on. For example, the interaction with the topography, the interaction with the environment, as well as the cold pool interaction with this deep cumulus plumes and organized convective systems. So it's a simple framework to understand a lot of convective system going on. You don't need the global model to understand the convection in general. In the diurnal cycle of a land situation, you get all kinds of convective system going on. And one by one, you sort of affect one to another. So the interactions among these convective systems does have a lot of impact on the afternoon thunderstorm precipitation or the convection the second day. So that means that we might need to know everything about this different kind of convective system to better simulate the diurnal cycle of convection. And that kind of errors without simulating the diurnal cycle is still a most challenging problems in the global model right now. Normally, though, these convective systems are not well simulated in the GCMs. So that kind of change in the evolution will change the cloud fraction, change the extreme precipitation, and so on, that has global impacts. And the other thing I like this diurnal cycle is that you don't need to simulate 100 years to get the results. I simulate like 1 day or 2 days. That's easy. Just 1 or 2. Just a short time, I can do a lot of simulations. So normally when we think about this, using a sounding to predict precipitation, we think of a parcel model based on a proof model type of thinking. So given an environment, I plotted in the black line here, I imagine a parcel that has starting from the boundary layer and following a moist eddy bed. And we can estimate how the convection can develop, the cloud top, the cloud base, or the strength of the convective system based on this potential energy generated, measured by the difference between the parcel and the environment. And this kind of setup or thinking has governed this convective system thinking in the past so many decades. We always use a cape to determine the strength of the convection, or use the thing, somewhat small here, the inhibition of the negative buoyancies to infer that the development of the convection. So this kind of model typically have a lot of trouble in simulating diurnal cycle. For example, here I'm showing the GCM simulation of diurnal cycle. The biggest problem is that when surface is heated up by sun, surface heating, you actually can get cape easily because you sort of change the starting point of the parcel. So, for example, if you are slightly warmer here, you get a lot of cape in this diagram. And in the model in GCM, we sort of translate this kind of cape potential energy into something. So the model has to start to working. So you see that everything starts at sunrise. So when the sun goes up, the rain starts to falling. And similarly, in different kind of model, H-line here, all the models have the similar behavior, except that the strengths might be different. And this kind of problem is sort of a known bias in the GCM for a long time. And we are trying to solve that problem by modifying this cape sync calculation or something else based on this plume model ideal concept. But back in the days, we found that actually what's going on is not the environment that sets up this parcel that perform this develop this convection. It's actually the series of development of the convection that triggered this afternoon thunderstorm. So here I'm showing that this around say 10 a.m. So the boundary layer already developed here. The black line showing here, and the red line represent the parcel model has a lot of cape, is warmer than the environment. But this average cloud points, the blue line here shows it's always colder than the environment. So it's actually stable in this a lot of cape condition. So what happened? Why this cloud doesn't go up? For naive thinking, you can think of this cloud, they are small, so they entrain a lot. They don't have enough energy to go up. So when they form, they can actually go out a little bit by condensation, but they can always be colder than environment because there are a lot of mixing from the environment. So we think that this cloud has a lot of work to do with the development of diurnal cycle when they actually modify the boundary layer environment. So here I'm showing that the time series of the cloud environment profiles. So you can imagine that the profile environment kept developing throughout the day by this modulation of these shallow clouds. The different contribution to the buoyancy sort of modify this environment differently. When these shallow clouds, they don't precede a lot, they tend to evaporate and cool the environment. So they modify the boundary layer stability, make it more unstable. Till some point when it's really unstable, then the convection can kick in. So this is what I'm trying to say, that the time evolution of this convective buoyancy interacting with the environment has a lot of, it's very important in shaping this diurnal evolution of convection. The other example is that if we imagine that this diurnal cycle have different size, patch size, or I mean the scale of these systems, it would produce very different scale of the precipitation. So imagine that you have a larger convective clouds here that will generate a lot of precipitating area. And this precipitating area actually interact with the land surface processes. So you might provide a horizontal scale that have a unique patterns of these surface fluxes. So imagine that you always develop convective system with any kind of scale. And if you get larger convective system or smaller convective system, the impact on the surface flux will that change the follow-up development of the next convection. So that's why I do this idealized simulation with using the random perturbation on this precipitation to have a different scale and strength of the perturbation to generate a set of surface fluxes so that have a different horizontal spatial scale. But overall, the mean average surface fluxes are the same. So in the GCA, you won't see anything different from the mean surface fluxes. But in a cloud resolving world, the surface flux has different patches that will have effects on the development of convection. So this is an example what the surface wind and precipitation looks like. The shading is the surface wind, so you see that conversion line here showing up in the larger patch, and not so much in the smaller patch here. So that's the precipitation in the black contour and the wind in the shading area. So I'm trying to change the horizontal scale of this patch size affecting the surface flux. And then we simulate the diurnal cycle with the surface flux to see how the convection responds within the day. So I sort of know predetermine the scale of the convective system as a 16 kilometer, 16 kilometer, or 2 kilometer, something like that. And you will see that in this figure, I show the structure of this wind circulation and based on this horizontal scale. And it's easy to imagine that if you have a different patch size with different surface flux, it will generate a horizontal circulation, something like this. And in that kind of circulation, it will sort of push the convective system at certain places with certain scales. And that kind of scale will impact the further development of the convective system. So with the surface flux patches produced by this precipitation, and you'll get the secondary circulation based on this surface flux difference. And then will generate a different scale of the convective system afterwards. So the statistics show here is that if you have a larger patch size generated by convective system, you actually get mean precipitation change quite a bit. It's about twice the amount of the compared to the no horizontal perturbation scale experiment. And you also get the extreme precipitation quite a bit. So here I'm showing this larger patch size can have about twice the impact of this extreme precipitation compared to the no perturbation scale. So you can imagine that the interaction with the surface and convection by these boundary layer processes can have a different impact on the boundary layer dynamics and generate different boundary layer circulation, so that the later influence on this convective system development and the follow-up precipitation and intensity of precipitation. So a simple test tells us that although we have the same energy input from this 256 kilometer box, typical of GCM grid size, but with a different horizontal structure within the convective system, we can have very different impact on this diurnal evolution of convective system, and especially the extreme. So I'll focus on that, and later on, the maximum precipitation, the precipitation peak in the diurnal cycle can be very intense. And if you can capture that, that will be a lot helpful in preventing this disaster in the landslide or something similar to that. Okay. So
can you show again how you would specify the patterns?
Oh, it's a very tricky experiment setup. So I use the average precipitation here, but I distribute it in a horizontal scale and strength of the perturbation into the each grid points of this. So this is 256 kilometer square domain. With each grid point, I use this formula to generate the actual precipitation this location really receive when over there at this point. So if I have a spatial scale about 64 kilometer, and this is a random perturbation from 0.1 to 1, something like that. And then we can decide we have a special patch of precipitation falling on this area. And the land surface model will calculate the surface flux according to only this random changes. Other parameters remains the same.
Okay, so and then you are using the land surface model flux to
drive the
okay.
So this is a two-stage development. Just try to separate the effects of the horizontal scales on this diurnal convection. Yeah, so after this kind of studies, I'm more confident that a random convection might be very difficult to predict. But if you know more about these boundary layer processes, maybe we can know more on this diurnal cycle evolution. That's sort of when I was in UCLA. Okay, so then I'm thinking about why does that matter? Why the boundary layer dynamics matters, and how do we treat the boundary layer dynamics better? And we get into this sort of given by Professor Alcala said, and you work on this model. So I am trying to dig out why this model can help me understand all these processes. So the model I use is so very different from other people is that it's a 3D vorticity equation. So it predicts the two horizontal vorticities. So this is, I don't know, eta and C, something like that. Two horizontal vorticities to represent the convective processes. And then in the right-hand side, you have the typical stretching and twisting effect. But what I'm trying to point out is that it shows the buoyancy gradient as an important sources of this horizontal vorticities. So that might be something very important in understanding the thermal difference that causes the circulation. And other things, including this is an elastic, so it doesn't include the sound wave to the simulation. It sort of simplifies this effect of sound waves and assume it's infinite speed, so that we don't have to treat with this pressure perturbations in this equation. And then the other way of saying that is that the effects of pressure perturbation sort of translate into the buoyancy in this equation set. And that'll be, yeah. So I'm trying to give an example on this simulation. So as I said, the vorticity is very responsive to this buoyancy gradient. This is the left-hand side is a typical image we see on this cloud resolving simulation. So we have the green is the amber cloud, and this the gray shading is the cloud itself. The blue dash is the rain. So you always see a big patch of clouds and raining in these numerical simulations. It give you an idea that this is pretty large scale circulation or large scale dynamics sort of controlling this simulation. But if you draw the buoyancy structure showing the right-hand side in the shading here, you'll see this small thermal chain structure here. So horizontally, the distribution will have a very different this small thermals interacting with each other, leading to a larger scale of this complete clouds. So from the beginning, the ideal plume-like development of the convective cloud might not be a good approximation of real convection, especially when the resolution is high. When I started the simulation with low resolution, say 2 kilometers, the convection is sort of big chunk of vertical velocity going up on the surface. Looks like a plume model, but when you increase the horizontal resolution to at least like 100 meters or higher, you'll see a lot of fine structure of this convection, especially this chain, this thermal chain structures mentioned by many others. And we think that this is essential for similarly convective system because the buoyancy gradient is actually the forcing generating these vorticities in this structure. So how do we get the big one? So here you'll see the left-hand side has a similar structure with the amber cloud and precipitation. But now the right-hand side, you see the buoyancy have aggregated into a larger chunk of convective system here. So you got a lot of big area of positive buoyancy and some cold top in the cold top. So the question is that how does that thermal chain structure sort of aggregate into the large coherent convective plume? So my explanation is that when you in a VVM, the vertical velocity is actually solved through this this equation. So this is actually using the definition of the vorticity twice and replacing the term with continuity equation. So the right-hand side is the curl of the vorticity, it's a ring vortex type of structure. The left-hand side is the equation form. So when you solve this equation, if you have it has a certain structures, the vertical velocity will sort of aggregate into a larger coherent structure based on this large scale pattern of this buoyancy structure. So I give you an example on this. So if I place a bubble, this is the diagonal structure. I place a big bubble in the domain center. So you get the buoyancy gradient here. So you generate this horizontal circulation vorticity here. Because we are in 3D model, so the buoyancy is in the circular form. So you got actually a ring vortex circling around this buoyancy here. I'm going to argue that this is an important structure for this aggregation of the convective system, so that as long as we form a large concentrated buoyancy structure, you can generate this associated ring vortex that can have a large scale behavior of this convective structure here. So this is the updraft, this is downdraft, and the lines represents the string lines represent the flow pattern associated with that. It's funny afterwards. Yeah. So you can see that the string line gets a larger and larger scale due to this coherent buoyancy aggregated together. Yeah.
What's the vertical scale that's being shown?
This is vertical. I think it's at 12 kilometer. So this is a pretty big plume there. So you can imagine that this represents the curve of the vorticity, and the solution looks something like that in a vertical velocity structure. You accept that? I'll go on to play the movie again. So I'm trying to link this equation. The right-hand side is the curve of vorticity, the left-hand side is the vertical velocity, solved by the elliptic equation. So the effect of the elliptic equation sort of smooths out this fine structure of the buoyancy or anything small scale vorticity, as long as you have a coherent structure there. And the most coherent structure in this case is a bubble. So you can see that the bubble has the concentrated circular shaped buoyancy, and that will generate this ring vortex associated with this convection. I think Yihong has saw this many times, but yeah, if I told you this is, will you buy it?
Kind of, but I just wasn't expecting that the updraft base is so wide in this case.
This
Yeah.
one?
Yeah. Or is it having some kind of negative values inside that?
Yeah. You see this?
Oh, okay.
Yeah.
Got it.
That's this 3D plotting that you can only see the surface. You don't see what's inside.
I think in a 2D solution, we actually see a single structure tilted in the bottom half of the cloud.
Yeah. And you're making the argument on the del -2 of the
Yes.
curl of vorticity, but you can also do it from the buoyancy, like Yihong had shown, like chunky buoyancy, and you smooth them first.
Yeah, so I'm trying to
And
link
then it's
Yeah.
interesting to think about, which is like the vortex ring is also an important conserved structure.
Yeah.
So,
But normally you expect to have a finer structure when you have high resolution. And then the big question is why we get a big cloud. That's hard to see from the higher resolutions, and you got smaller pieces of the convective structure showing up in this simulation. But later I found that as long as you get a larger patch of this bond structure, you always get this convective system associated with this bond structure. And then again, the curve of this one sort of form this vortex ring, and this is important coherent structures that sort of sustain by itself. Yeah. If I say it's a tropical cycle, would you believe that? Something like that.
If you can show something, but just to keep an eye on time, we
Yeah.
have about 15 to 20 minutes.
Okay.
Even the rate stuff.
Okay, it's okay. The most important figure is shown here. That's it. Yeah. So I want to
Since that's the most important figure, let's talk about it.
okay, thank you.
In what sense is this not a plume?
Oh no, I'm saying that this is a plume. Yeah, that's what yeah. That's exactly my point. But when you have high resolution, you kind of hard to find a plume. And then
If you look at the vorticity,
yeah. And then it's a plume again. Thank you for pointing that out.
I'm trying to control myself that I don't think flume is well defined, especially in moist convection community.
Yeah.
But that's another.
that's a
That's
lengthy discussion.
Yeah, but I like the way that when you go higher resolution, you cannot find a plume, but sometimes you get a plume when you get the correct structure linked together. Okay, so I'm going to speed up a little bit. So I sort of try to extend this idea of this model development with implementation of topography here. So what I do is try to implement this boundary conditions in the model so that as a forcing in the vorticity equation here. And the major how do I determine the forcing is to assume that the boundary of the velocity is 0 at this point. So I can calculate that the point forcing of this vorticity by definition of vorticity and add it back into the vorticity equation so that flow can follow. And then the velocity actually is determined by solving this equation down here. So again, the W equation has a kind of filtering effect on filtering out the small scale structures, but retaining the larger patterns of this vorticity structures implemented by these point forces. And what I meant is that normally when we treat the topography, you only dealt with the adjacent point of the topography here. So this point is being considered as when you approach this topography, but we add more layers here to have a finer structure so that the approaching will be smoother. But in this kind of non-local solution of the vertical velocity, you actually get this topography effect sort of solved instantaneous as a structure when it's far away from this topography. Before it sees the topography, it knows it needs to go up and go down afterwards. Okay, so this is the proof of concept that everyone does for this implementation of topography. I was asked by the reviewer to do this. I don't know why, because they say that sometimes when you have this is a tracer at the top of the domain, the topography is here, no interaction. When you advect it with the wing here, you're expecting the concentration tracer to move by a constant velocity like that. And this is a very challenging task for atmospheric models, particularly in this CDR models of this weather prediction models. They do something like this. because the coordinate is transformed using the by the numerical methods. So the tracer moving toward a mountain generally have been twitched, sort of stirred up by this only the change of the topography. So you're expecting the errors like this. So when the tracer moving from left to right, you're getting a lot of noise result over the mountain area. So it makes it very difficult to study the flow of a complex topography right on the topography, because you normally get this kind of very massive stuff. But when you sort of solve it using this this edit point forcing approach, you get only this typical numerical error caused by the numerical scheme. So you see nothing here, nothing like this. So this is the time when I learned that why in Taiwan we learn a lot of we study a lot of tropical cyclones, but we never studied when the tropical cyclone is on Taiwan. We only study when it's passing by or the tracks, because when it's on Taiwan, you got a lot of noise. It cannot be separated from the physics based on these numerical errors. So, example showing you that how complicated this flow interacting with the topography can be. So we have a flow going like this, just going this way. Normally, you're expecting a upslope flow and downslope flow over there based on this flow regime, but you see that there are multiple structures associated with this flow and generated by this so complicated topography here. So it doesn't have to be lifting in the upwind region. It doesn't have to be subsiding in the downwind region. We have a very complicated structure shaped by this topography. So I think it's important to point out that the way we treat the topography and using the vorticity equation is an essential approach in simulating flow over the complex topography like Taiwan.
Sorry, what's being contoured exactly?
Is
Is it only the
vertical velocity?
Is it only the part that's associated with the?
Yeah.
Like it's not penetrating up.
It's only
there.
this. I didn't decide the details. It's only the topographic effect solving by this equation. Yeah. So I put the forcing on the right-hand side to generate this figure showing how the vertical velocity will look like with this kind of upwind condition. And it's pretty nice that normally the flow is going in here and producing very complicated interaction with the fog and precipitation in the mountain area.
Is the vertical penetration of the contour? Is partly set by the width of the upward forcing area, and partly by something measuring its magnitude.
Yeah, so again, the magnitude is sort of only a contour line, so it doesn't have the full spectrum of the contour. And it's very interesting that how the movement sees the upstream flow is kind of complicated in this situation. So I see this as a solution of this elliptic equation. So with this upstream flow, this is a real case simulation. So with this upstream flow, you can generate vertical velocity like this, just simply by implementing the point force in the model to get this vertical velocity. And it's very complicated. Okay. So I developed the Taiwan VVM in Taiwan that has to have Taiwan, and that has to have some kind of land surface processes because I want to simulate diurnal cycle. And then the other thing I didn't talk about today is microphysics, but it's also very important. Oh, let's skip that. So here's the simulation after thunderstorm in Taiwan. Normally, you expect that the after thunderstorm sort of last till like the afternoon, right? But this one is, you see a time here, it can last till almost midnight. And it's kind of typical in Taiwan that we have afternoon thunderstorms lasting till 10 p.m. And then everyone's expecting, is it going to rain more or is it going to stop? So interaction between the land sea breeze, the upslope flow with the complex effect of the topography, the microphysical processes, everything together. Yeah, it looks nice to have capture cases like this. So following this idea, we do a global warming simulations based on the soundings we selected from the summertime typical Taiwan soundings here. And what I want to say is that if we have this environment that's set up by this topography, the effect topography can determine the precipitation. We only need to change the upstream soundings so that the model feels a different kind of environment. And we can say, how does that change in response to this change of the soundings? And then we interpret the change of the sounding as a slow global warming, meaning that we only modify this temperature profile by adding 3K. 3K is a typical number. It represents 2015 or 2018, depending on the scenarios you use. But anyway, you will always get plus 3K at some point. Right now it's like 0.3 something. And then we got the two sets of environment I can use to drive the model. Okay, I switched this before. So the first thing I'd like to tell you that the most exciting figures, because in the past I didn't want to compare with the observation. But right now I choose only 30 ensemble simulation. The left-hand side is about a few hundred observation results. And I'm showing the precipitation. This is stations in Taiwan. It's very dense. Yeah, but you can see that over this foothill of the mountains, somewhere here, you can see that the match pretty well. And the most important things about the dino cycle evolution, the timing match perfectly with the observation. Although I only use a sub-ensemble set, I didn't do the full simulation of this. Two applications.
Is this under a certain type of weather regime?
Yeah. It's a dino cycle dominant. There's no typhoon, no fronts, no big synodic events going on here. So if you match the two figures together, you'll see that they are inline most of the places. And I even try to argue that the purple one, the extreme precision produced by the model, is actually in between of this observation. There is a mountain top. We don't have a site over there. And we don't have a lot of station on the east side, but you see that there are a lot of this extreme precipitation going on in the east side of this Taiwan island. So I can do some statistics. The number I use is extreme. And I mean very extreme.
Excuse me for interrupting. That I have a student meeting I have to go to. That last slide was very impressive.
This one?
The one before. That one.
Okay, thank you.
Congratulations.
Okay. It really. So this is the statistics I choose to demonstrate the current climate and future climate, possibly global warming situation. I choose a very extreme cases. So this is 100 millimeter per hour. Can you imagine that? Not here, right? But it's sort of typical in Taiwan. We got 100 millimeter per hour cases, a lot. Yeah, we were sort of a place that has very extreme precipitations. And that means that this extreme precipitation has influence on this mountain area, landslides, or the good part, the water supply for the dam. And you see that this is the current, this is the future. A lot of the more intense cases and more sort of shifted toward the plain area. Something like this. So again, some statistics just showing you that the extreme red is the future sort of shift toward this plain area downhill, and they sort of extended. And what is used for? I try to sell this to the government. I think I tell them that this is robust results, right? Because the orographic is there. The environment I set for this dinocycle convection is very simple, just changes of global warming. But the impact is very, very, very big. First of all, the red also involve the changes of the extreme precipitation in the future. And the good side, it covers a lot of water dam here. And this is a biggest water dam in Taiwan. But the bad side is that it covers a lot of places that potential for landslide or other debris flows here. So this provides, I think, useful guidance for these changes in the future. And this also provides a useful guidance for model intercomparison, because we have observations in Taiwan, very complicated, very dense network. We have physical models, and we can choose some of this high resolution global storm result model from NICAN or ICON or other things to see how they behave in this kind of setup, dino cycle convection over land. And we see that they behave quite different, and they have different biases. The good news is we can diagnose more to see what's going on in the ICON or NICAN model. And then the more important thing is we can compare with the observation to see how this kind of simulation really captures the precision hotspots in Taiwan.
And then nighttime is at a couple of kilometers, and your simulation is at?
Yeah, mine is like 500 meters. This is like 3 kilometers. These two are 3 to 5 kilometers for the NICAN and ICON. So you see that it's more pixelated here. Oh, but I think the data is regret to 10 kilometers.
It's considering that these are both kilometer scale models.
Yeah. They simulated.
They both know what the topography is. It's a little worrisome that there's such difference between them.
Well, there are more details on these models.
Mm-hmm.
For example, these models cannot really implement such complex topography. Yeah, they're causing some problems. So they'll smooth it out. Something like this. Yeah. So they don't really have the true topography in the beginning. And the most important thing is that some of these hotspots are not captured well. Yeah, this is something I'm going to collaborate with NICAN and ICON to help them set up this in the comparison to understand what's going on.
How did you represent the topography?
Yeah. In VVN, I use this point forcing added to the flow. But in NICAN and ICON, they both use the term following coordinates, so they use the coordinate transform of the equation. So that will cause some numerical problems, and they have to smooth it out, something like that. So that there are a lot of problems in the complex topography, and they have different tricks in treating this event.
Is VVN one of the few models that use high coordinates?
I guess in LES, they all use high coordinate.
In LES,
Almost every one of them. But in regional models, they use pressure coordinate, sigma coordinate.
And we're running up to the like scheduled end time of the seminar, so we may start to lose audience members.
Thank you so much.
Okay, so so if you are going somewhere, just feel free to.
And only like 3 slides away.
Okay, but
Yeah. So just give you an idea that what I think about AI. So in the beginning, I found everyone think this is AI talk. Because the topic is sort of AI generated field. But really, I want to say is that if we have a good enough physical model, we can do the emulator. So the development is sort of like a 2 parallel lines. We keep developing the physical models. We can also develop the AI models. The AI model takes the data from the physical models and learn from them. And then we can accelerate this process by a particular specific type of weathers in Taiwan. This is very important because if we want to talk about, say, something like this, we need to talk about specific weather regimes, afternoon thunderstorms, tropical cyclones, or other things, fronts, anything. It's hard for us to sort of come everything together and give a score, say, oh, this is the model that's very well or bad, because each weather regime, they have different issues and the performance will be very different. The more important thing is that we measure the afternoon thunderstorm by precipitation, but we can measure the errors in other situations by flow or other type of parameters. It's hard to say give everything good situations. So using this kind of scenario-based approach, we sort of generate a lot of data sets for specific weather regimes. For this one, it's an afternoon thunderstorm. It's leaf vortex type simulations. We generate a lot of leaf vortex type simulations, and the data can be used as an emulator. So we do this, then we can have an AI model that simulates the leaf vortex situation with a good structure and fast calculation. And then we kept improving the physical model and improving the AI model. Together, we can get a better prediction of what's going on in Taiwan. And I need 10 more minutes on this slide, but again, this is what I did is using an autoencoder type of structure. So it projects the data into 2 latent dimensions here. So in the latent dimensions, I can try to interpret what's going on with this latent space. And then I found out that we found out that this latent space actually means the upstream flow direction and speed. Very straightforward. So we can use the latent dimension to construct dependence on the input wind speed and direction. So this is the physical interpretable situation of this latent dimension. So I can give a point with upstream flow, say 2 kilometers per second and northeasterly. I can generate a flow pattern like this. So you sort of have an explainable framework by mapping this emulator to low dimensional the latent dimension, so that you can generate this flow pattern easily based on your input wind direction and wind field. And furthermore, if we use a more complicated AI model, you can capture the diurnal cycle better. And again, we sort of interpret this as an emulator of this Taiwan VBN, the physical model. As we improve on this physical model, we can trust this AI model better. Okay, so yeah, I guess that's it. So can sounding predict local weather? Yeah, this sounding is very complicated. But if we can do the physical model and doing a lot of simulation, maybe we can learn from the AI model by our understanding and by the model, and we can do this prediction based on this AI model for what's going on in Taiwan.
What's the difference between the not quite lower right and the very far lower right? The
Sorry?
two
Different type
shadings on.
they are all precipitation, but they represent two precipitation regimes. This is the afternoon thunderstorm. This is like a
Southerly flow.
southwestern flow. Yeah, you know Taiwan better than me.
And these are predicted by the,
Yeah, this is I'm trying to do in the next few years. Okay, that's it.
thank you. Yeah, so that's